Right, so far in this chapter, we've been looking at rate laws, which tell us about the rate versus the concentration. Today, I'm going to talk to you about integrated rate laws, which tell us about the relationship between concentration and time. And this is more useful to us in the lab because those are the things that we can more easily measure. And so I've started this first slide with a table that summarizes the relationship between the rate law and the integrated rate law and the plots that you get. There's something similar in your textbook, but I thought this one was really nice. So it can be a good study tool if you need it. So first, let's take a look at a zero order reaction. And we learned in the last video that the rate is equal to just the rate constant K, right? It doesn't depend on the concentration of the reactants. And so to get to the integrated rate law, all you do is integrate using calculus. I'm not going to go through those steps because I know not all of you have taken calculus, and the steps don't really matter, but you do need to know that the yellow, or the equation in the yellow box here, is what we get. That's the zero order integrated rate law. Okay, and what that looks like if we plot it is we have the concentration of A on the y-axis and time on the x-axis, and this equation looks very much of the form y equals mx plus b. So if that's the case, then b is our y-intercept, so A naught, which is our initial concentration, is where our plot is going to start up here. All right, and then as the reaction progresses, we're just going to get a straight line that comes down, and the slope of that line is going to be the negative of the rate constant K. So anytime you see a plot that's concentration versus time and you have a straight line, then you know that you have a zero order reaction. For a first order reaction, just as a review, the rate law is equal to rate equal to the rate constant K times the concentration of A. So when we integrate that, you end up with the natural log. Again, I'm not going to go through the steps for calculus, but just recognize that or associate the natural log with a first order reaction. And so if we look at this part here as being in the form y equals mx plus b, then our y-axis is going to be the natural log of the concentration of A. Our y-intercept is going to be the log of the initial concentration. And then when we make the plot, we're going to get a straight line. The slope of that line is going to, again, be the negative of the rate constant K. And we're going to get a straight line when we plot the log of the concentration versus time. That's a first order reaction. Finally, for a second order reaction, our rate law is the rate equal to K times the concentration of A squared. When we integrate that, again, this looks like the form y equals mx plus b, so our y-axis is going to be 1 over the concentration of A. Our y-intercept is going to be 1 over A naught. And then our reaction, the plot will actually go this way because it's 1 over A naught. So as the concentration gets smaller, 1 over A is going to get bigger. And then in this case, our slope is going to just be the rate constant K. And then one last thing I want to mention is using these integrated rate laws, it becomes a lot easier to figure out how much of a particular product is going to be left over time and things like that, because we're plotting concentration versus time. And so one other thing that is interesting to look at is the half-life, which is often abbreviated T1/2. And that's the amount of time required for the concentration of a reactant to fall to 1/2 of its initial value. So if you start with 1 molar of the reactant, that would be how long it takes to get to 1/2 molar. If you start with 2 molar, it's how long it takes to get to 1 molar. And the only one that we're going to be looking at half-life for are first order reactions, and that's because it just so happens that the half-life for a first order reaction is constant, so it doesn't matter what your initial concentrations are, the half-life is going to be the same. And the equation for that is T1/2 is equal to 0.693 over K, or K is the rate constant. This might look like a complicated equation. It is on your equation sheet. You do not have to memorize it, but you do need to remember that it only applies if you have a first order reaction. Now let's take a look at some examples of how we can use this new information. So here we have a plot obtained for the reaction SO2Cl2 goes to SO2 plus Cl2. So this is a reaction where we just have one reactant and it's breaking apart into two pieces. So here we have a plot of the log of the concentration of a reactant versus time. And so given that this is the log, that should automatically signal to you, or just hopefully will soon signal to you, that this must be a first order reaction. So the integrated rate law that goes along with this is going to be of the form the log of A is equal to minus KT plus the log of A naught, which is our initial starting concentration. Okay, so what you can see from this is that since we now know that this is a first order reaction, our rate law is going to be equal to the rate equal to K times the concentration of SO2Cl2 to the first power, because this is the first order reaction. And looking at the equation that's with our graph plus the form I just wrote down here, you can see that the rate constant for your reaction is going to be 0.000290 inverse seconds, because this is first order, right? And if in part C, it's asking you if you repeat the reaction with 0.5 molar SO2Cl2, how much remains after 45 seconds? And so all we need to do to find the answer to that is plug those two numbers into our integrated rate law and solve for the concentration when we put in 45 seconds for the time. So that's going to be the log of SO2Cl2 is equal to minus 0.00290 times 45, because that's our time, plus the natural log of 0.500, which is our starting concentration of reactant. I'm not going to spend a lot of time solving this. If you have questions about how to solve equations with the natural log, you can come see me, but I know a lot of you have covered that in math already. So when we solve that, we get that the concentration of A is equal to 0.494 molar. And so you can see that in 45 seconds, not a whole lot of it reacts. Okay, so for number 2, we have another plot. This time our plot is 1 over the concentration. So it's of the form 1 over A is equal to KT plus 1 over A naught, which is our starting concentration. Anytime we see 1 over a concentration, that should tell you that this is a second order reaction. So the rate law is going to be rate equals K times the concentration of NO2 squared, because it's second order. And the rate constant for the reaction is going to be 0.255. That's there in our graph. And again, if you begin the reaction with 0.750 molar NO2, how long will it take until half of the reactant has been consumed? And so here we just want to plug in 0.750 for the initial concentration, and if half of it has been consumed, then our final concentration is going to be 0.375, so you can plug that into our equation, and we're going to solve for T. Again, I'm not going to spend a lot of time on the math here, but we get a value of T equal to 5.23 seconds. All right, our third example is the following reaction is represented by a first order integrated rate law. And the reaction is CH3CN goes to CH3NC. If the rate constant at 500 degrees Celsius is 0.0462, and our units here are hour to the minus 1, plot the concentration of CH3CN as a function of time to yield a linear graph, assuming you begin with an initial concentration of 0.50 molar CH3CN. Okay, so if we have first order reaction, you should automatically think the natural log. So our y-axis is going to be the natural log of, I'm just going to write A, but it's the natural log of C3CN. And then our our x-axis, is going to be time, and in this case, our units are going to be hours because that's the units that the rate constant is in. All right, so our initial concentration we'll plot here, and it'll be the natural log of the initial concentration. So the natural log of 0.50 molar is negative 0.693, so that's that unit on our y-axis, and we're going to get a straight line going down, right, and the slope of that line is going to be negative 0.0462 because that's our rate constant. So if we're going to write the equation for this line, it's going to be y equals negative 0.0462 times t plus the natural log of 0.5, which we just said is negative 0.693. Right, so that will be the graph for this particular equation. The last thing I'm going to talk to you about today is the effect of temperature on reaction rates. And you should know just from life experience that generally as we increase temperature, the reaction rate goes up, and that's because K goes up. And the reason this happens is because if we increase the temperature, then two things happen. One, the molecules have more kinetic energy, and so they collide with more energy. And they also, when they're moving more quickly, are more likely to collide. So both of those factors cause the rate of the reaction to go up. Right? So today I'm going to talk to you about the factors that influence this. We talk qualitatively about the things that have to happen according to collision theory for a reaction to happen. Today I'm going to talk to you about the activation energy and also the transition state. So the activation energy is the amount of energy that's required to get over that hump in order for a reaction to proceed. And so this really is what determines how fast a reaction happens. So the larger the activation energy is, the slower the reaction is going to be because it's got a bigger hump to get over. So like if you're climbing a mountain, the bigger the mountain is, the longer it's going to take you to get over it. Right. The transition state, which is also sometimes called the activated complex, is the molecule is a state that the molecule goes through that's higher in energy that gets it from the reactants to the products. And so we'll talk to you a little bit more about that in class and give you some examples of that. You basically just need to know that the transition state is a higher energy complex that the reactants go through if they're going to get to the product state. Okay, and what I've shown here is a diagram that shows, which should look familiar to you because we've looked at delta H before. So delta H tells you the difference in energy between the reactants and the products. That tells you whether the reaction is thermodynamically favored or unfavored. What I'm talking about today is the activation energy, which is this energy here. Okay, and then if a reaction is going to go backwards, so in order for it to go forwards, the reactants have to go up over this pump and back down. If a reaction is going to go backwards, and we're going to talk more about reversible reactions in the next unit, but they would have to go back up this direction and back. So the activation energy, since this is an exothermic reaction, the activation energy to go backwards is going to be higher than the activation energy to come forward. All right, so let's consider if we have H2 plus I2 going to 2HI. The delta H for our reaction is 18 kilojoules per mole, so that's a positive number, so we know this is going to be an endothermic reaction. So as we go from the reactants to the products, we're going to go up in energy, and that difference is going to be 18 kilojoules per mole. Right, our activation energy for the forward reaction is very high. It's 211 kilojoules per mole, so this is not going to be quite to scale. But if we were to draw it, it's going to go up very high, and this energy from here, to the top, is going to be 211 kilojoules per mole. And then if we wanted to look at the activation energy to go backwards, that would be the energy from here to here, and that's going to be the difference between the two, which is 193 kilojoules per mole for this particular reaction. Okay, so this is how you would draw an energy level diagram given that information. This is something you're almost definitely going to see, at least on this unit test, but highly likely on the AP test as well. Right, now draw the reaction energy diagram for the following reaction. If the enthalpy of reaction is negative 199.8 and the activation energy is 10. So I'm going to ask you to pause it here, draw the reaction energy diagram, and then replay, and I'll go over the answer and hopefully they agree. Okay, so hopefully you've done it at this point. So the enthalpy of reaction is negative, so that tells us that we're going to go down in energy as we go from reactant to product. Okay, and the activation energy is quite small, actually. It's only 10, so relative to the 200 of the other one, it's going to be a pretty small hump that has to be gotten over. So just to review, this energy difference from here to here is 199.8, and this little energy difference right in here, I don't know if I can even draw in here that small, is only 10 kilojoules per mole, but that's what the activation or the energy diagram looks like for this particular reaction. Okay, and now the last thing I'm going to show you is the Arrhenius equation, and it is a quantitative way to link the rate constant with temperature and activation energy, because both of those things play a role. You do not need to know this equation, nor do you need to know how to do any calculations with it. I'm only presenting it because it gives all of the factors that influence whether or how fast the reaction is going to happen. So EA is the activation energy. So I already told you a big activation energy means a slower reaction. A small activation energy means a fast reaction. The frequency factor is a measure of the number of times that the reactants approach the activation barrier per unit time. So how often do they have enough energy that they could get over that barrier? So that, again, is going to be related to the temperature in some ways, because the more often that happens, or the more kinetic energy they have, the more likely that is to happen. And then the temperature is also present in the exponent of this equation, and so that also plays a role. So just to summarize, we talked qualitatively about the fact that you need a collision to happen, you need the molecules to be in the proper orientation, and you need them to have enough energy. And this equation gives you a quantitative way to relate those things, although you do not have to use it to do any calculations.